Hello, everyone, and welcome. My name is Eustace Asangawa, and I am Principal Program Manager for Internet of Things Security at Microsoft. Co-presenting with me today are Paul Howard from ARM, Evid Park from Scalys, and Femi Idowu from Microsoft. Today, we present the Enclave device blueprint for confidential computing at the edge. I shall begin with making the case for confidential computing and introduce what we mean by the Enclave device blueprint. Paul and Yvette will walk you through the blueprint architecture, components, and actual realization into a real device. Finally, Femi will share information on where and how you can experience and engage the Enclave device blueprint. But first, let's understand what we mean by confidential computing. The Internet of Things and intelligent edge computing is experiencing exponential growth, and with that comes the need for confidential computing. Confidential computing entails protecting data at rest, in transit, and most importantly, when in use. This is in stark contrast with traditional computing where data is protected at rest, in transit, but not when in use, thereby exposing the data to attacks during its use. For the highest protection, confidential computing leverages tamper-resistant hardware isolations to provide trusted execution environment, or simply enclaves. Next, let's see why confidential computing is important. The fast evolution in edge computing continually transforms our relationship with data and thus raises the need to always protect data, especially when in use. By leveraging trusted execution environments, or enclaves, confidential computing can offer data protection in two fundamental ways. First, confidential computing can help ensure that data in the form of intellectual property, privacy data, and compute workloads, including artificial intelligence, is only accessible to the right owners. Secondly, confidential computing protects the compute environment for safety. As edge computing grows in intelligence such as autonomous control of sensitive operations like self-driving cars, or of critical infrastructure like the power grid, protecting the compute environment becomes extremely crucial for safety and hence the growing need for enclaves. Now, let's see how we plan to make confidential computing mainstream for the intelligent edge. The nature of confidential computing demands the right infrastructure for tamper-resistant isolation of confidential workloads. Cloud solution providers build and operate these infrastructures for their customers to deploy confidential workloads in the cloud. For edge computing, the solution builder must provide their own infrastructure in the form of capable devices. Capable devices for confidential computing at the edge are devices with trusted execution environments that can resist all tampering, including physical tampering. We call these devices enclave devices. Enclave devices are lacking in supply and so holds back the proliferation of confidential computing at the edge. Enclave devices are not a new concept. Historically, they've been used in very niche industries and government departments. Luckily, they've existed long enough for us to understand why they continually elude mainstream adoption, despite the high demand for it in edge computing. Primarily, the engineering, operation, and maintenance of enclave devices is arduous in complexity and cost, thereby limiting accessibility to very few organizations. Our goal is to change this posture by enabling solution with the enclave device blueprint. The enclave device blueprint is a combination of guidance, projects, and resources to enable a community approach to developing and servicing enclave devices. It also includes resources for deploying confidential workloads at scale. We believe this community approach will allow us to share efforts and bring confidential computing at the edge to mainstream. We will present a real example composed of ARM technologies running a Linux operating system and deployed through Microsoft Azure Cloud. However, the Enclave device blueprint is agnostic to technology, operating system, or cloud. All software components are currently in open source, and we envision complete community ownership of the Enclave device blueprint in the long run. With this overview, I shall now turn over the presentation control to Paul. Paul, please take it away.
Thanks, Eustace, and hello everyone. My name is Paul Howard, and I'm a Principal System Solutions Architect with ARM. Confidential computing is really about the emergence of a new security boundary in computing. Security boundaries define how our assets are protected, and we build security architectures around them. Now, we are very used to building applications securely because they need to be signed, and those private signing keys need to be protected, for example. But with confidential computing, we want to be able to execute our applications within a secure boundary as well. We want strong isolation of those workloads relative to the operating system and relative to other workloads. And then once we have that, we can couple these notions of secure build and confidential execution together to create this very compelling end-to-end flow where our applications are protected everywhere, even when they are executing, just as we can see there in the diagram on the left. So what are the technologies that enable this new secure boundary? What are our enablers of confidential computing? If we take the ARM architecture just as an example, there is confidential compute architecture, or the CCA, which is the future vision to protect all data and code wherever computing is happening. Now, CCA is part of the ARM v9a architecture. It was made available earlier this year, and devices based on that architecture will begin to emerge over time. But if we want to look specifically at what is available in devices today, then there is also the ARM Trust Zone technology, which is hardware-enforced isolation that is built into the CPU, and which is available in devices such as the Scalys TrustBox Edge 201, which is the device that we're showcasing today. And then alongside processor architecture, there is also platform security architecture, which is a framework that governs and ultimately certifies our overall system design, ensuring a hardware root of trust and an assessed set of best practices to ensure security in depth from the chip all the way to the application. And then, lastly, as Eustace mentioned, we need blueprint. We need an overall architecture that brings these and similar enabling technologies all together, both on the device and in the cloud, and actually allows us to realize their value end to end and at scale in an IoT edge computing deployment. But let's start with the device. So let me hand over to Evert at this point to introduce the Scalys TrustBox Edge 201.
Thank you, Paul, for the introduction. My name is Evert Pap. I'm a solution architect at Scalys. To build a confidential device which is ready to be used by a customer, the OEM must provide certain features on the device. In this context, the device is a piece of hardware securely provisioned with software. As we are promising confidential compute on the edge, we need both hardware security and software attestation. On top of this secure edge device, we run the confidential packaging system and leverage the Azure cloud infrastructure to allow secure deployment at scale. Most of these requirements are covered by the ARM System Ready certification, and we'll cover more details in the rest of this presentation. The TrustBox Edge 201 is an example of such a device. It's based on an NXP device, an LS1028 processor. It uses the NXP Trust architecture, which leverages the ARM Trust Zone. It's also equipped with TPM, which adds another level of trust to the hardware. I'll give the stage to Paul for more details on the blueprint.
Thank you, Evert. So that is the Scalys TrustBox Edge 201. So let's now have a look at the additional components of the overall solution for confidential computing at the edge. So to kick off then, first of all, we have these new things that we call confidential packages. This is a binary file format, and it will have an open and portable specification. This is going to give us a convenient way to bundle our confidential applications for secure storage and transport. And where we have a file format, of course, we also need some tooling. So again, we are developing new tools in open source that will allow us to build these new confidential packages in our CI pipelines, and then to process them on the target device. Once they reach the target device, there is a confidential package manager, which runs in a secure enclave on the device and enables the workloads to be installed, decrypted, and executed. And then, across all of those build and installation steps, there are key management designs and protocols. And these are based on common, proven public key cryptography practices. There is also lots of flexibility in them so that people can adopt their own preferred key provisioning and key lifecycle mechanisms. So let's look at solution architecture. And when I talk about solution architecture, I mean exactly that. I mean the device, which we've talked about, but I mean the solution around the device as well. So this is the end-to-end solution, which spans across our build pipeline, across our cloud infrastructure, and of course, across those important secure computing devices with their support for confidential enclaves. Now, the goal of the solution is to be able to build a confidential application in our build pipeline and to publish and store that confidential application to the cloud, and then finally to deploy and to execute it in a secure enclave on a device like the Trust Box. But the goal is to do all of that in such a way as to never allow the confidential application to have its contents revealed until it is in the enclave and executing. And alongside that, we have some additional goals, such as wanting the solution to be very portable and very agnostic with respect to platforms and technologies. And we also want to make as much use of proven scalable mechanisms as possible, such as container repositories, such as digital twins, and such as serverless functions. One critical feature of this design is the sharing of a common symmetrical encryption key to both the build pipeline and the target device, so that the build pipeline can produce an encrypted application that the target device can decrypt and execute. This key can be protected at all times by storing it securely in a suitable key vault in the cloud, and also by wrapping it with additional encryption whenever it is transported. But even with all of this protection, we want to go further. So we only use this shared key once, when the application is first deployed to its target device. Now, shared keys of this kind are commonly called class keys, and once the application reaches its target device, it's going to be re-encrypted. It will be re-keyed using a new key that is completely tied to the hardware of that single specific device and never leaves it. This use of a class key is one of the factors that enables the solution to scale to a large number of devices. So this picture gives an overview of how the components interact, but we're going to understand it better by actually walking through a demonstration and seeing the various steps in action. So let me hand back over to Evert now, who's going to walk us through the demo.
Thank you, Paul. So in the next set of slides, we'll present a demo of the blueprint in action. As it's not very enlightening to see the box itself connecting to the cloud and provisioning itself, we go to the relevant parts of the system. This will explain the different parts of the blueprint and how they translate to an actual implementation. A more technical demo and deep dive can be found on the resources that are part of this presentation. So the DevOps, or cloud side of the demo, leverages the familiar and proven technology of the Azure cloud. We use IoT Hub for device management, the Key Vault for secrets or key storage, the function app to bridge between them, and the container registry for actual deployments of the modules. For this demo, we use the Scalys TrustBox Edge 201 as the device. This is the newest member of the TrustBox Edge family, and it's also the first to get system-ready certification. If we look at the solution architecture, the only new features in the cloud system is the key distribution. We've solved this by using existing and proven technologies like the Key Vault and the Device Twin services, and connecting them together with Azure functions. For this demo, we'll assume that we have a device registered to our IoT Hub. Preferably, this will be done by using the TPM registration, but pre-shared certificates or a connection string is also an option. The logic to connect the devices and the key vaults must be defined. This is done using the Azure functions. Later in this presentation, there will be more information on how to do this, but for now, we just keep the high level and don't worry about the technical details. Next, we'll make sure that we can actually access the key vault. In this example, it's a simple ACL scheme, but the system allows for fine-grained access control. Our current implementation scheme uses a class key to encrypt the Enclave payload. This class key is generated by the key vault with the provision key function. After the provision key function is called, a new secret is available in the key vault and identified by the ID we just provided. The architecture is flexible, allowing you to provision a key manually or use a managed HSM and import your own key. The second step of the confidential deployment of our Enclave is to provide a way for the device to securely retrieve this class key. The class key is wrapped using the public key of each device. This is done by the distribute key function. The class key can be only unwrapped by the package installer running on the device as a system-level trusted application. This means the key is never exposed to the untrusted environment. The keys are exchanged between the cloud and the device using the device twin features of Azure. When the device connects to the IoT hub, it will report its public key as a device twin property. This property is then picked up by the function distribute key. This will use the public key to wrap the class key and export the wrapped key as a device twin property. This property is then available for the device. The wrapped key is provided to the package manager running in the trusted execution environment, which decrypts the application. It will re-encrypt it using the device internal unique key, tying it uniquely to the hardware. To deploy a confidential workload, we first need to actually develop and build one. In this demo, we're using the Open Enclave SDK. This helps development of enclaves and associated host application by abstracting away a lot of the complex enclave-specific details. The applications are distributed in a container, and the confidential application is an encrypted part of this container. The decryption key is not part of the deployment, as this is provided by the device twin side channel, as previously explained. So with the Visual Studio IDE, we provide a development environment. It uses Azure IoT and Open Enclave plugins to get a uniform and familiar development environment. The application can be debugged and tested locally using QEMU and similarly deployed to the actual target device. At this point, we have a mechanism in place to distribute keys and a module that has the confidential application. The last thing we need to do is set up deployment of the module to our device. In this demo, we're deploying to a single device, but this can be easily scaled to a fleet of devices using the group deployments. For the previous demo to work, we assume that we have a device ready to run our workloads. This puts some requirements on the device. We need the infrastructure in place to actually do the work, and of course, we need to trust the device as it's running our confidential application. Running it on an untrusted box kind of negates the whole goal. The device needs to have both the trusted execution environment, OPTI in this case, and the confidential packages manager running on top of it. We also need IoT Edge runtime and a container runtime. The host OS on which it's running is less critical, but for our demo, we have both a Yocto and Armbian option. Which OS is used for real deployment can differ, but we recommend using either a hardened Yocto build or a binary Linux release tailored for long-time support. To finalize our demo, we built a confidential application that uses machine learning to identify our company's logos. The demo is available to be reproduced, and the final piece to allow a complete end-to-end confidential deployment. From developer through the cloud to the device, the entire chain is available in our resources section. We have a limited supply available of our TrustBox Edge 201, which can run this demo out of the box. But of course, you can also adapt the system and deploy it on your target of choice. I now hand it over to Femi, who will talk about how to get the actual demo and the resources.
Thank you, Evert. Hello to one and all. My name is Femi Dowu. I'm a Senior Solutions Architect at Microsoft. In this section of the presentation, I will be sharing some information with you regarding how to locate and leverage the resources we have made available to the wider community in the context of the Enclave Device Blueprint project. The resources for the project have been consolidated on the Microsoft GitHub repository known as Azure Samples, which I will take a moment here to present to you. So, what is Azure Samples? Azure Samples is an official Microsoft repository that provides a centralized experience for code sample discovery with the following goals in mind. Firstly, it offers a singular location where both developers and other customers can go to discover samples for any Microsoft tool, product, or service. Secondly, the Azure Samples repository offers a flexible means to access source control on GitHub that keeps pace with ongoing community contributions made on GitHub to empower the developer experience. And finally, it makes it easy for partners to be a part of the new code discovery experience and distribution site. Now, I'd like to briefly touch upon what a code sample is. So, the code base located on Azure Samples is code that is meant to provide examples, programs, and libraries with the purpose of educating developers on how to build basic functionality that enables them to eventually create more complex applications. Now, moving on to the topic of what the Azure Samples repo comprises, the basic building blocks comprising Azure Samples are, firstly, the backend services. These ensure that customers get access to the latest version of code samples thanks to index-driven searches across code sample repositories hosted on GitHub, thereby optimizing their product as well as code search and discovery experiences. The second building block in the chain is represented by the samples GitHub code repositories. These are individual repositories that contain code samples hosted on GitHub. And finally, the third and final building block in the chain is represented by the customer-facing front-end experience, which is otherwise known as the Samples browser. The Samples browser is located on the Azure Samples project homepage. The Azure Samples project homepage is therefore the one-stop location where customers can find relevant code samples by searching or applying either product and/or programming language filters to perform the search. Now, moving on to the next slide, here I will spend a moment with you to explain what resources will be available to you in the context of the Enclave Device Blueprint project itself, as well as how you can leverage the resources using the tools previously mentioned, and finally, explain what accessing these resources will mean for you. So, what does accessing the Azure Samples repo mean for you in the context of the Enclave Device Blueprint project? Well, it means we have a number of collaterals curated for you on the Azure Samples GitHub repository for the Enclave Device Blueprint project. The team would like to extend an invitation out to you to visit the project repository using the link which you can find in the resources section of this presentation in order to download and experience the full end-to-end demo, gain access to the Enclave Device Blueprint components, including the source code, so that you can replicate the solution, and finally, access the resources link to the white paper, blogs, and other community resources. And with that, I will now hand over to my fellow presenter, Eustace, to close out today's session. Thank you for your attention. Over to you, Eustace.
Thank you, Femi. And there you have it, folks. We presented the Enclave Device Blueprint with actual physical realization in TrustBox Edge 201. We also provide a wealth of resources on Azure Samples to enable immediate engagement. We now invite device builders and solution developers to experience the Enclave Device Blueprint. We also invite decision makers to now factor in confidential computing workflows in their respective undertakings for their digital transformations, given that we have this possibility now. The URL on this page will lead you to all information and resources. We've also prepared granular navigation guides to specific interest on this resources slide. Thank you so much for your attention. There is a live Q&A session starting now to continue the conversation. To take part, join us on Zoom by clicking the yellow button just below the video player on this session's page.